Hello there, and welcome to this slow exploration of the distant outer solar system. Tonight, we'll journey far beyond the familiar planets, past the realm of Neptune, and into a region of cold, icy worlds that most people have never heard of. These are not the planets you learned about in school, at least not in the traditional sense. They are dwarf planets, and the worlds beyond Pluto represent some of the strangest, most distant objects that orbit the Sun. Many of them are so far away that the Sun appears as just another bright star in the black sky. These worlds exist in a region of profound darkness and cold, where temperatures drop so low that gases freeze solid and become part of the landscape. Some spin so rapidly that their shape becomes warped and strange. Others travel on paths so extreme that they venture almost to the edge of the Sun's gravitational influence. No spacecraft has ever reached most of them. No human has ever seen one up close. Yet through patient observation and clever detective work, astronomers have managed to discover their secrets piece by piece from here on Earth. If you find yourself curious about these distant, unknown realms, settle in, breathe deeply, and let us explore them together, one quiet revelation at a time. To understand what makes a dwarf planet different from other objects in space, we first need to understand what astronomers actually mean by the term. A dwarf planet sounds like it should be a small version of a regular planet, something that never quite grew up enough to become fully formed. But that is not quite right. A dwarf planet has a specific definition that was created by the International Astronomical Union in 2006, and it is based on three distinct characteristics rather than simply size or mass. First, a dwarf planet must orbit the Sun. This separates it from moons, which orbit planets instead, and from objects that drift freely through space without a clear path around any star. Second, a dwarf planet must have enough mass for its own gravity to pull it into an approximately round shape. This is a property called hydrostatic equilibrium, and it requires a world to be large enough and solid enough that gravity wins over the resistance of the material. A small asteroid held together by solid rock alone, with no internal heating or deformation, can keep an irregular shape forever. But if an object grows large enough, gravity pulls equally from all directions and squeezes it into something roughly spherical. That roundness is the signature of a world massive enough to shape itself. The third characteristic is the one that truly sets dwarf planets apart from full planets. A dwarf planet has not cleared the neighborhood around its orbit. A full planet, by definition, has either gobbled up all the other debris in its path through gravity, or has knocked it aside so forcefully that the region around its orbit belongs to it alone. A dwarf planet, by contrast, orbits in a region crowded with other icy bodies and small worlds. It shares its orbital space with many companions, which means it never achieved gravitational dominance. This is why Pluto was reclassified from a planet to a dwarf planet in 2006. Pluto orbits in the Kuiper Belt, a zone filled with thousands of other icy objects. It never cleared that neighborhood, so it failed to meet the modern definition of a planet. The demotion of Pluto from a full planet to a dwarf planet was not a small matter. Pluto had been known since 1930, discovered by Clyde Tombaugh at Lowell Observatory in Arizona. For 76 years, it held the status of the ninth planet, the mysterious distant world at the edge of the known solar system. Children memorized its name along with Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Pluto was in textbooks, in popular culture, in the minds of millions of people, as a legitimate planetary member of our cosmic neighborhood. But the discovery of larger and larger objects in the outer solar system, particularly the discovery of Eris in 2005, forced astronomers to confront a fundamental question. What exactly is a planet? If Pluto deserved to be called a planet, then so did Eris, which was actually more massive. And if both of them were planets, then the dozen other similarly large objects in the Kuiper belt probably deserved the title too. The solar system suddenly seemed likely to have 15, 20, or even more planets, not 9. The International Astronomical Union faced a choice: either expand the definition of planet to include all these distant icy worlds, or create a clear, consistent set of rules that would exclude them. They chose the latter path. The creation of the dwarf planet category was not meant as an insult to Pluto or as a demotion in any emotional sense. Rather, it was a practical solution to a scientific problem. By creating a clear definition based on physical characteristics, astronomers could finally classify objects consistently and meaningfully. Beyond Neptune, the solar system becomes a region of mystery and cold. Astronomers call this vast zone the Trans-Neptunian region, meaning beyond Neptune. Within it lies several distinct populations of icy bodies, each with its own characteristics and its own story to tell about how the solar system formed and evolved. The best known of these populations is the Kuiper belt, a donut-shaped zone of icy objects that extends roughly from Neptune's orbit around 30 astronomical units from the Sun out to about 55 astronomical units. An astronomical unit, or AU, is the average distance from the Earth to the Sun, roughly 150 million kilometers, or 93 million miles. The Kuiper belt is home to thousands of known objects, perhaps tens of thousands more, that remain undiscovered. Most of them are small, ranging from icy chunks a few kilometers across to bodies several hundred kilometers in diameter, but a few are large enough to qualify, under the modern definition, as dwarf planets. These Kuiper belt objects are composed mostly of frozen volatiles: methane ice, ammonia ice, air ice, and nitrogen ice, mixed with darker materials and rock. They are remnants of the solar system's formation, preserved in deep freeze at great distances from the Sun, where the cold is nearly absolute. Beyond the classical Kuiper belt lies the scattered disk, a more distant and dynamically active region where objects follow more extreme orbits, some highly inclined or very elongated. Objects in the scattered disk have been knocked into unusual paths by gravitational interactions, probably with Neptune, during the early chaotic period of the solar system's history, when gravitational dynamics rearranged the entire architecture of the outer planets. Some of these scattered disk objects reach enormous distances from the Sun, farther than any Kuiper belt object, and at the very edge of this region, beyond even the scattered disk, a few objects follow such extreme paths that they are called detached objects, having been removed from any clear gravitational influence and following their own lonely trajectories through the darkness. The story of Eris is the story of how modern astronomy transformed our understanding of the solar system in a single moment of discovery. On January 5, 2005, an announcement stunned the astronomical community. A team of researchers at Palomar Observatory in California had discovered a new trans-Neptunian object that was not only large, but appeared to be larger than Pluto itself. The discovery team consisted of Mike Brown, a planetary astronomer at the California Institute of Technology, Chad Trujillo of the Gemini Observatory, and David Rabinowitz of Yale University. They had been conducting a systematic survey of the outer solar system, searching for distant icy bodies by carefully comparing repeated photographs taken on different nights and looking for objects that moved lowly against the background of stars. When such movement was detected, it indicated that the object lay far from Earth and was likely to be in the outer solar system. The challenge of detecting such distant objects is profound. Eris shines by reflected sunlight alone, and at nearly 10 billion kilometers from the Sun, that reflected light is incredibly faint. The discovery required not only careful observation, but also sophisticated image processing techniques to identify the slow motion of a distant body against the field of more distant stars. The object they discovered was given the provisional designation 2005 EV96, but the team gave it an informal nickname, Sedna, after the warrior princess from television. The name proved prophetic because the discovery of Zen, soon to be officially named Eris, would trigger a conflict that shook the foundations of planetary science. The International Astronomical Union was forced to answer a question that had been sidestepped for decades. What, fundamentally, is a planet? The debate that followed led directly to the 2006 decision to create the dwarf planet category and to reclassify Pluto. For astronomers and the public alike, this was a moment that revealed the power of discovery to reshape scientific understanding. Eris is a world of extremes. With a diameter of approximately 2,326 kilometers, it is slightly smaller than Pluto when measured by diameter, but it is significantly more massive. The mass difference is crucial. Eris weighs about 27% more than Pluto, which means it is denser and composed more heavily of rock and metal beneath a thin layer of ice. This density tells us something important about how Eris formed and what materials make up its interior. The world is not a loosely packed collection of icy snowballs, but rather a coherent body with significant rocky material and perhaps iron in its core. Eris follows one of the most extreme orbits of any large object in the solar system. It travels on a path that is both highly elongated and tilted sharply relative to the plane in which most planets orbit. This means Eris does not stay at a constant distance from the Sun the way Earth does. Instead, its distance varies enormously. At its closest approach to the Sun, called perihelion, Eris reaches a distance of approximately 38.5 astronomical units. At its farthest point, called aphelion, it travels out to nearly 97.5 astronomical units from the Sun. This means the distance from perihelion to aphelion is nearly 60 astronomical units, a vast gulf of space separating the two extremes of its orbit. A single complete orbit takes 561.37 Earth years. This means that Eris was last closest to the Sun around the year 1898, and it will not return to Theia Forbist. If Phoenix, that Eris was last closest to the Sun around the year 1898, and it will not return to Theia Forbist. Point again, for another 400 years. Right now, Eris is moving slowly away from the Sun, gradually heading back toward aphelion in the far reaches of space. As Eris approaches perihelion during its long journey, surface ices warm enough to sublimate, to transform directly from solid to gas, and may briefly form a thin atmosphere before freezing again as the dwarf planet retreats into the deep cold of the outer solar system. The surface of Eris is covered in a rich mixture of ices, primarily methane and nitrogen, which reflect about 96% of the light that reaches them. This extremely high reflectivity means that Eris appears brighter than fresh snow on Earth, a dazzling white world in the black emptiness of space. This reflectivity makes Eris one of the brightest objects. Their story goes back much further than most people realize, and it began not with intention, but with accident. Around 10,000 years ago, Eris has a moon named Dysnomia, which orbits the dwarf planet in a path that is nearly circular. The moon was discovered through observations made at the Keck Observatory in Hawaii and elsewhere, and it was officially designated as the moon of Eris. Dysnomia is named after the daughter of Eris in Greek mythology, the demon goddess of lawlessness and discord, a fitting name for a moon orbiting a world already named after the goddess of discord herself. The moon is small, with a diameter estimated at about 150 kilometers, making it a significant body relative to its parent, though still tiny by the standards of Earth-sized moons like our own moon, which is over 3,000 kilometers in diameter, or Mars's moons. Dysnomia completes an orbit around Eris, roughly once every 16 days, traveling through space at a distance of approximately 37,000 kilometers from the surface of the dwarf planet. To put this in perspective, our moon orbits Earth at a distance of about 380,000 kilometers, so Dysnomia is much closer to Eris than our moon is to Earth. This moon is believed to be composed largely of frozen water. The presence of Dysnomia has proven invaluable for astronomers. By carefully observing the moon's orbit and measuring how long it takes to complete a full revolution around Eris, astronomers can apply the laws of orbital mechanics and gravity to calculate the total mass of the Eris system. This is one of the most important techniques for measuring the masses of distant objects in space. Before Dysnomia was discovered, astronomers could only estimate Eris's mass by making assumptions about its composition and density. Once the moon was identified and its orbital characteristics measured, the mass calculation became much more certain. This allowed astronomers to make direct comparisons between Eris and Pluto and to understand the internal structure and composition of both worlds more clearly. The measurement revealed that Eris is indeed more massive than Pluto, despite being slightly smaller in diameter, confirming that these two dwarf planets have different internal structures and compositions. The extreme orbit of Eris reveals something profound about the outer solar system. The scattered disk, where Eris travels, is not a quiet, orderly region where objects follow gentle, predictable paths. It is a place where gravity has written a chaotic history into the present orbits of distant worlds. Early in the solar system's formation, about 4.5 billion years ago, the outer region was turbulent and dynamic in ways that astronomers have only recently come to understand. The giant planets, Jupiter, Saturn, Uranus, and Neptune, migrated from their original positions, pulled by gravity in collisions with smaller bodies. As they moved, they scattered smaller objects outward and inward, some into the asteroid belt between Mars and Jupiter, some into the Kuiper belt beyond Neptune, and some, like Eris, far beyond into the scattered disk. This migration process is often called the grand tack, referring to the idea that the planet's migration resembled the zigzag path of a ship tacking through the wind. As they moved, the giant planets shepherded countless smaller bodies, some toward the Sun and some toward the outer edges of the solar system. The highly eccentric and inclined orbits of objects in the scattered disk are the fossil record of this ancient chaos. They tell the story of a violent rearrangement that occurred long before the Earth was fully formed. Eris, with its extreme orbit, is a living example of this history. The world carries within its current trajectory the memory of encounters with the giant planets billions of years in the past. The world that altered astronomy is itself a testament to the solar system's turbulent past. Ice is not simply frozen water, at least not in the world beyond Pluto. On these distant dwarf planets and candidates, ice exists in varieties that are difficult even to imagine on Earth. Water ice is certainly present, just as it is on moons and comets throughout the solar system. But on the distant cold worlds, water ice behaves differently than it does here. It becomes as hard as rock, frozen at temperatures so low that it cannot sublimate under normal conditions. The crystal structure of ice changes at extremely low temperatures, creating different phases of ice with distinct properties. But water ice is only one component of these frozen landscapes. Methane ice, the frozen form of the gas that makes up much of natural gas on Earth, covers significant portions of Pluto, Eris, Make, and other distant dwarf worlds. Nitrogen ice, frozen nitrogen gas, also appears on these worlds, particularly on Pluto, where it forms vast glacial plains. Carbon monoxide ice and ethane ice have been detected spectroscopically on some of these bodies. These volatile ices are rare on Earth, where such substances exist only as gases. But in the outer solar system, at distances where the sun's heat is so faint that it barely warms the surface, these materials freeze into solid form. These ices exist in equilibrium with the faint, cold emptiness of space. On Pluto, the surface temperature averages around 238 Kelvin, or about minus 35 degrees Celsius, or about minus 30 degrees Fahrenheit. On Eris, the temperature is even lower, estimated at around 212 Kelvin. At such temperatures, substances behave completely differently than they do on Earth. Methane becomes hard and brittle. Nitrogen, which is a gas in our atmosphere and makes up most of the air we breathe, becomes as solid as rock. The presence of these various ices can be determined from Earth through spectroscopy, a technique in which astronomers split the light reflected from a distant body into its component colors and wavelengths. Different materials absorb and reflect different wavelengths, creating a unique fingerprint that allows identification even from billions of kilometers away. This technique has been crucial for understanding the composition of distant worlds. Make was discovered on March 31, 2005, making it one of the 3 large trans-Neptunian objects found in the early years of the 21st century, alongside Eris and Haumea. The discovery was made by Michael E. Brown, Chad Trujillo, and David Rabinowitz, the same team that discovered Eris. These discoveries, during the first few years of the 21st century, fundamentally changed how astronomers viewed the outer solar system. Each new large object raised new questions about how many such bodies might exist, and whether the solar system really contained only 9 planets, as people had been taught for generations. When first found, Make was given the provisional designation 2005 EF9, and the discoverers nicknamed it the Easter Bunny, perhaps because of the timing of the discovery, or because of whimsy common among astronomers. Astronomers sometimes use informal nicknames for objects before official names are assigned, and these nicknames can reveal something of the personality and culture within the scientific community. Later, when the object was officially recognized as a dwarf planet, it was given the name Make, after the creator deity of the Rapa Nui people of Easter Island. The name honored both the unofficial Easter Bunny nickname and the International Astronomical Union's rules for naming classical Kuiper Belt objects after creator deities from various world mythologies. Make is the 4th largest dwarf planet in the solar system, with a diameter roughly 60% that of Pluto, making it considerably larger than Earth's moon. It orbits in the classical Kuiper Belt, a region where objects follow relatively stable, nearly circular paths and low orbital inclinations. This makes Make fundamentally different from Eris, which travels on the extreme scattered disk orbit with its dramatic eccentricity and inclination. The classical Kuiper Belt is considered a more primordial region, with objects that have remained relatively undisturbed since the solar system's formation, suggesting that objects here preserve more of the original composition and properties from the solar system's early days. Make is the 2nd brightest object in the Kuiper Belt after Pluto itself, reflecting a significant fraction of the sunlight that reaches it across nearly 4 billion kilometers of empty space. This brightness indicates that its surface is covered with highly reflective materials, primarily ices, that scatter light efficiently. The contrast between the bright, icy surfaces of these dwarf planets and the darkness of space makes them visible as point sources of light, despite their vast distances from Earth. Astronomers can detect them only because of their high reflectivity and the sensitivity of modern telescopes. The surface of Makemake appears reddish-brown when observed from Earth, a coloration that suggests the presence of darker, complex organic materials mixed with the brighter ices. These organic materials, often called tholins by astronomers, are produced when ultraviolet radiation from the Sun, or perhaps cosmic rays from space, strike the surface ices and alter their chemistry, producing more complex carbon-based molecules. Spectroscopic observations have definitively identified methane ice and ethane ice on Makemake's surface, indicating a composition similar to Pluto's, but with its own distinctive chemistry. The proportions and distributions of these ices differ from Pluto, suggesting different conditions during formation or different evolutionary history. Scientists have detected pellets of frozen methane as large as half an inch in diameter, resting on the icy surface. These would be produced if methane gas sublimated into the thin atmosphere and then refroze at the surface, much the way frost forms on extremely cold objects on Earth, but at a much larger scale. The process requires cyclical heating and cooling, suggesting changes in surface conditions over time. Makemake has an extremely low surface temperature, estimated at around 40 Kelvin, or about -233 degrees Celsius. This makes Makemake one of the coldest places in the solar system, rivaling Pluto and Eris in the frigidity of its surface. Despite its distant orbit and minimal solar heating, Makemake may develop a thin atmosphere of nitrogen gas near its closest approach to the Sun, when perihelion allows some small increase in temperature. The world does not currently approach perihelion, so if an atmosphere exists, it is currently in a frozen state, part of the solid surface. However, this atmosphere, if it exists at all, would be extraordinarily tenuous even at perihelion, far thinner than the atmosphere of Pluto, which is itself barely detectable from Earth. Makemake has a moon, discovered in 2015 and provisionally designated as S2015-13647121. The Moon is commonly called MK2, informally by astronomers, a simple designation that distinguishes it from its parent body. The discovery of this moon, like the discovery of Dysnomia around Eris, provides a crucial tool for measuring the mass of the system. Once the Moon's orbital characteristics are well understood, calculations based on gravitational interactions will reveal the total mass of Makemake more precisely than current estimates allow. The Moon itself remains poorly characterized, a tiny companion to a distant world, observable only through the most powerful telescopes on Earth and astronomical satellites. Its exact size remains uncertain, estimated to be somewhere between 150 and 300 kilometers in diameter. Though this range reflects considerable uncertainty, its composition can only be guessed at based on limited spectroscopic data and assumptions about whether it resembles the parent body or has a completely different nature. The discovery of Makemake's moon demonstrates that even small, distant dwarf planets can possess moons, raising questions about how common such satellites are in the Kuiper belt. And scattered disk, the existence of moons around many dwarf planets, suggests that the formation processes that created these distant worlds often produced multiple bodies rather than single isolated objects. It also shows that astronomers continue to make discoveries in the outer solar system, even as existing knowledge about known objects remains incomplete. Each new discovery opens new questions and challenges existing assumptions about the nature and architecture of the Trans-Neptunian region. Haumea is perhaps the strangest dwarf planet in the outer solar system, a world so unusual in its properties that it seems almost alien by comparison to other bodies. Haumea spins with incredible rapidity, completing one full rotation in approximately 4 hours. This is faster than the rotation of any other large body in the solar system. To put this in perspective, the Earth takes 24 hours to rotate once. Jupiter takes about 10 hours, and even the quickly spinning asteroids in the inner solar system take many hours or longer to complete a single rotation. Haumea's 4-hour day is extraordinarily fast for such a large body. At the equator, this rapid rotation creates centrifugal forces that act against the gravitational pull holding the world together. These competing forces deform Haumea away from a spherical shape, stretching it into an elongated triaxial ellipsoid, a shape somewhat like a football or an egg standing on end. The exact dimensions of Haumea have been difficult to pin down precisely, as it has never been visited by spacecraft and appears only as a point of light, even through the most powerful telescopes on Earth. However, stellar occultation observations, made when Haumea passed in front of a distant star and briefly blocked its light, have allowed astronomers to measure Haumea's size and shape more accurately. These observations represent a clever technique. As Haumea's edge crosses in front of a distant star, the light from that star is gradually blocked, and the pattern of blocking reveals the shape of Haumea's profile. By observing from multiple locations on Earth simultaneously, astronomers can construct a detailed map of the dwarf planet's silhouette. These observations suggest Haumea has dimensions of approximately 2,386 kilometers at its longest axis, making it roughly the same size as Pluto, but with a distinctly non-spherical form. The rapid rotation of Haumea is a puzzle that astronomers have worked to explain, and the explanation points to a violent past. The rapid rotation of Haumea is so extreme that it suggests the world experienced a massive collision in its past. When two large bodies collide in the outer solar system, the impact can knock debris loose, creating moons and fragments, while simultaneously spinning up the remnant body. The discovery of Haumea's two moons, Haumea and Namaka, provides circumstantial evidence for this collision scenario. The larger moon, Haumea, measures approximately 310 kilometers in diameter, while the smaller moon, Namaka, is about 170 kilometers across. Both moons are named after goddesses in Hawaiian mythology, reflecting Haumea's own Hawaiian name. The discovery of these moons in 2005, made using the Keck Observatory telescopes atop Mauna Kea in Hawaii, was a major discovery in outer solar system astronomy. Beyond the moons, further evidence emerged in 2017 when an international team announced that Haumea is surrounded by a ring system, the first ring system ever discovered around a trans-Neptunian object or dwarf planet. The ring has a radius of approximately 2,290 kilometers and a width of roughly 70 kilometers, with an estimated opacity of about 50%, meaning it partially blocks light passing through it. The ring is composed of frozen particles that rotate around Haumea, 3 times slower than the dwarf planet itself rotates. The rapid rotation and elongated shape of Haumea are thought to be consequences of the same collision event that created the ring and the moons. The impact not only spun up the world and deformed it into an ellipsoid, but also blasted debris into orbit, where some fragments coalesced into the observed moons. Other fragments may have formed a disk of material that eventually settled into the current ring system. This collision, if it occurred as hypothesized, would have been catastrophic and dramatic. altering the entire character of Haumea forever. The collision would have occurred billions of years ago, early in the history of the solar system, when such impacts were far more common. The remnants of that ancient event persist to the present day, making Haumea not merely a world, but a monument to violence in the distant past. The discovery of Haumea's ring opened a new avenue of understanding about rings in the solar system. Rings were previously thought to be found only around the giant planets, Jupiter, Saturn, Uranus, and Neptune, and around a few small asteroids in the inner solar system. The presence of a ring around a dwarf planet suggested that rings might be more common in the outer solar system than previously believed. This single discovery expanded our expectations of what might be found among the distant icy worlds. This discovery has led astronomers to re-examine other distant bodies, wondering whether additional ring systems might exist around Kuiper belt objects and scattered disk dwarf planets, waiting to be discovered through future observations. The search for rings around trans-Neptunian objects has become an active area of research, with astronomers planning campaigns to look for the telltale signatures of rings around other large dwarf planets and candidates. The Haumea collision family represents a remarkable case study in outer solar system dynamics. When the impact event occurred that created Haumea's unusual properties, the collision also produced fragments that remain in Haumea's vicinity even today. Several other trans-Neptunian objects follow orbits similar to Haumea's and display spectroscopic and compositional similarities, suggesting they are remnants of the same collision. These objects, collectively called the Haumea family, provide astronomers with a window into the past, allowing study of material that was excavated from Haumea's interior during the ancient impact. The fragments range in size from small bodies, just a few hundred kilometers across, to larger members comparable to the known moons. By comparing the properties of family members, astronomers can infer details about Haumea's internal composition and structure. If the collision excavated material from deep within Haumea, the composition of the fragments should reflect that deep interior. The family also demonstrates that large collisions in the Kuiper belt, though probably rare, do occur and can have profound effects on the objects involved. Such collisions would have been more common billions of years ago, when there was more debris in the solar system and impacts were more frequent. The existence of well-defined collisional families associated with dwarf planets shows that the outer solar system has an active, if slow-paced, history of impacts and dynamical evolution. This history continues to shape the architecture and composition of the Trans-Neptunian region, even billions of years after the solar system's formation. The story of the Haumea collision family is the story of a single catastrophic moment that sent echoes through the ages. The two moons of Haumea remain among the most intriguing objects orbiting any dwarf planet in the outer solar system. Haumea, the larger of the two, measures approximately 310 kilometers in diameter, making it a substantial moon by the standards of the distant Kuiper belt. Namaka, the smaller companion, spans roughly 170 kilometers across. Both travel in nearly circular orbits around their parent world, which is unusual given that impacts and collisions often create chaotic, eccentric lunar orbits. The orderliness of their current paths suggests that either the collision event that created them was somehow gentle enough to leave stable orbits, or that the moons have since settled into their current regular motion through tidal interactions and gravitational evolution over billions of years. Haumea orbits farther from Haumea than Namaka, at a distance of approximately 10,000 kilometers, while Namaka travels closer to the primary, at a distance of about 3,400 kilometers. This arrangement, with one moon close and one farther away, is typical of systems where a collision created multiple fragments of varying sizes. The ring system surrounding Haumea adds another layer of complexity to this world. The ring rotates 3 times slower than Haumea itself, a mismatch that astronomers continue to try to understand. If the ring and moons all formed from the same collision event, why do they have different rotation rates? One possibility is that the ring material was created more recently than the moons through a smaller impact or through gradual collisional grinding of debris in the system. Another possibility is that the ring's rotation rate has changed over time due to interactions with the moons or with solar radiation pressure. The brightness and density of the ring, revealed through stellar occultation observations, tells us that the particles are composed of frozen water, much like the moons themselves. Particles in the ring range in size from dust grain dimensions to chunks several meters across, forming a structure far more delicate than the dense rings of Saturn, but nonetheless real and measurable. The discovery of Haumea's ring was so surprising that astronomers have begun searching more carefully for rings around other trans-Neptunian objects, and preliminary results suggest that rings may indeed be more common in the distant solar system than anyone previously suspected, waiting silently around worlds that few have studied in detail. The naming of dwarf planets follows traditions established by the International Astronomical Union, and those traditions reflect something about how astronomy as a science honors both discovery and cultural diversity. When an object is confirmed as a dwarf planet, the International Astronomical Union decides on an official name, but the path to that name often passes through multiple stages. The object first receives a provisional designation, typically a number and letters indicating the year of discovery and other details. Astronomers working on the discovery often use informal nicknames, which sometimes become well known in scientific circles before an official name is ever assigned. These nicknames can be charmingly eccentric. The object that became Eris was nicknamed Sedna, after a fictional television character. Make, before its official name, was called the Easter Bunny because of its discovery in early spring. These unofficial names are never used in scientific publications, but they persist in the community and sometimes appear in popular articles and in the memories of those who followed the discoveries. The official naming process is more formal and deliberate. For Kuiper Belt objects, including dwarf planets, the International Astronomical Union has established guidelines. Classical Kuiper Belt objects are named after creator deities from world mythology, while scattered disk objects are named after underworld deities. This system was designed to create a meaningful taxonomy that also honors the mythological traditions of many cultures. Pluto is named after the Roman god of the underworld, appropriate for its location in the scattered disk. Eris is named after the Greek goddess of discord, a name that proved prophetic given the celestial controversy the object's discovery sparked. Haumea is named after the Hawaiian goddess of fertility and childbirth, reflecting both the cultural significance of the Hawaiian Islands and the creative implications of the collision that created Haumea's distinctive features. Make, the creator deity of Rapa Nui in Easter Island, connects both to the spring timing of its discovery and to the International Astronomical Union's naming conventions. These names anchor the dwarf planets, not just to scientific discovery, but to the cultural heritage and mythological traditions of human civilization. They remind us that even in the coldest, most distant reaches of the solar system, the objects we discover become part of our shared human story. The dwarf planet candidate Gong represents one of the most distant and reddest known objects in the outer solar system. Gong was discovered in July of 2007 by American astronomers Megan Schwamm, Michael Brown, and David Rabinowitz, using the Palomar Observatory Survey Telescope in California. though the discovery announcement did not come until January of 2009. The delay between discovery and announcement is common in modern astronomy, as astronomers spend time confirming observations, calculating orbits, and verifying that a newly found object is truly new, rather than a previously discovered object misidentified. Gonggong's name comes from a water deity in Chinese mythology, making it one of the very few dwarf planet candidates to be named after an Asian mythology. Making it one of the very few dwarf planet candidates to be named after an Asian mythological figure. The name is fitting, given the object's connection to the deep, cold waters of the outer solar system. The dwarf planet candidate is massive, with a diameter estimated at approximately 1,230 kilometers, making it the fifth largest known trans-Neptunian object. Gonggong orbits in the scattered disk, far from the orderly classical Kuiper belt, in a region where gravitational chaos shapes the trajectories of distant worlds. Its orbit is both highly eccentric and highly inclined, meaning it follows an elongated elliptical path that also tilts sharply relative to the plane in which most planets orbit. At perihelion, Gonggong approaches to about 33 astronomical units from the Sun, while at aphelion, it retreats to over 101 astronomical units. This mess means Gonggong spends most of its orbital period in the deepest cold of the outer solar system, far beyond the more familiar Kuiper belt objects, taking approximately 700 years to complete one full orbit. One of the most striking features of Gonggong is its distinctive red color, a shade that immediately distinguishes it from the more neutral gray and white tones of other distant objects. Spectroscopic observations reveal that the dwarf planet's surface is covered with reddish material, likely tholins produced by the interaction of ultraviolet radiation and cosmic rays with simple ices on the surface over billions of years. Water ice is also present, along with other frozen compounds that absorb different wavelengths of light, in ways that create Gonggong's characteristic crimson hue. The presence of both water ice and evidence of possible past cryovolcanic activity suggests a complex geological history, though whether any activity continues in the present remains unknown. The slow rotation of Gonggong, with a period of about 22 hours, indicates that this world rotates more gradually than Haumea does, but more quickly than many other distant objects. Gonggong possesses a known moon called Xianglu, which orbits the dwarf planet and provides an opportunity for astronomers to calculate its mass through orbital mechanics. The name of the moon, also drawn from Chinese mythology and meaning nine-headed serpent, continues the cultural theme of Gonggong's naming tradition. The dwarf planet candidate, Kawawa, holds a distinction that was surprising when first discovered. It possesses a ring system. Kawawa was found in 2002 and is a large classical Kuiper belt object with a diameter of approximately 1,110 kilometers. The discovery of Kawawa was made during systematic surveys of the outer solar system, the kind of careful, patient observation that has led to the identification of most known dwarf planet candidates. Kawawa's name comes from Tongva mythology, referring to the creator deity of the Tongva people who inhabited the region of present-day Los Angeles and Southern California. The moon of Kawawa, called Weiwot, is named after Kawawa's son in the same mythology. When observations revealed the presence of a ring around Quaara, announced through stellar occultation data in 2023, it created substantial interest in the astronomical community. Rings around distant objects are rare and difficult to explain. The classical explanation for why rings exist around giant planets involves the Roche limit, a distance below which a moon will be torn apart by gravitational forces if it ventures too close to its parent body. The fragments from the destroyed moon eventually spread out to form a ring. However, The rings of Quaoar appear to exist well outside the classical rush limit for that dwarf planet, suggesting either that the particles are held together by their own internal gravity, creating a kind of rubble pile behavior, or that the ring was created through a different mechanism entirely. One possibility is that the ring material is recent, created by a collision between objects in Quaoar's system after the Roche limit calculations that would have destroyed them billions of years ago. Another possibility is that the ring materials have unusual properties that allow them to survive beyond where conventional predictions suggest they should be torn apart. The surface of Quaoar appears to show water ice and other frozen compounds, spectroscopically similar to other classical Kuiper belt objects, but with its own distinctive composition. The presence of a ring system and a moon makes Quaoar one of the most complex dwarf planet candidates known, a miniature version of a planetary system with multiple structures and orbital elements to consider. Among the most peculiar and distant dwarf planet candidates is Sedna, a world that travels in one of the most extreme orbits known to any large object beyond Neptune. Sedna was discovered in 2003 during a survey by astronomers using the Samuel Ossian Schmidt telescope at Palomar Observatory, and it was named after the Inuit goddess of the sea and marine animals. The name proves fitting in ways that transcend mythology, for Sedna's orbit is as unusual and remote as the icy depths of the Arctic waters from which the goddess emerges. Sedna's diameter is estimated at approximately 995 kilometers, making it a substantial object and a leading candidate for dwarf planet status. However, Sedna's mass remains uncertain because no moon has been definitively detected orbiting it, which means astronomers cannot use the orbital dynamics of a satellite to calculate the world's mass precisely. The radius of Sedna's orbit from the Sun is approximately 576 astronomical units at aphelion, making it by far the most distant known dwarf planet candidate. In contrast, Pluto's aphelion is only about 49 astronomical units from the Sun, and even Eris, with its extreme scattered disk orbit, reaches only about 97 astronomical units. Sedna ventures to more than 5 times the distance of Eris at its farthest point. The perihelion of Sedna, its closest approach to the Sun, occurs at a distance of about 76 astronomical units, still vastly farther than any of the more famous dwarf planets. This means that Sedna never ventures close enough to the Sun to receive substantial heating. Even at perihelion, the Sun would appear as nothing more than a very bright star in the dark sky, providing virtually no warmth. The surface temperature of Sedna remains perpetually in the range of about 40 Kelvin, among the coldest places in the known solar system. The orbital period of Sedna is perhaps its most striking characteristic. This distant world takes approximately 11,400 years to complete a single orbit around the Sun. This means that Sedna was last closest to the Sun during a time when human civilization on Earth was still in the early stages of the Stone Age, long before written records, before agriculture, before cities. When Sedna returns to perihelion again, it will be the year of approximately 13,500. The timescale of Sedna's orbit is so vast that it is difficult even to conceptualize. Human history, the rise and fall of civilizations, the development of technology, all of recorded human experience spanning thousands of years, represents only a tiny fraction of Sedna's orbital period. An entire age of human development, from the Stone Age through the present, would occupy less than 1/100th of Sedna's year. This extreme orbital period tells us something profound about the architecture of the outer solar system. An object with such a distant aphelion and such a long orbital period must have undergone some process that sent it into this extremely remote trajectory. The classical explanation involves gravitational interactions during the early days of the solar system, when the giant planets were still migrating and rearranging the outer regions of the planetary system. As Neptune and other planets moved, they would have scattered smaller objects outward, some to even more distant reaches than Sedna currently occupies. Sedna's current orbit suggests that in the past, it may have ventured even farther from the Sun before being scattered back inward by interactions with other objects, or with the gravitational influence of passing stars. The extreme remoteness of Sedna and objects like it suggests that the solar system extends far beyond the more familiar planets and even beyond the objects typically thought of as the edge of the system. The mystery surrounding Sedna's distance and its origins has prompted considerable scientific speculation. At such a vast distance from the Sun, Sedna cannot have always been in its current orbit. Calculations of gravitational dynamics and orbital mechanics suggest that no process occurring within the solar system, as we understand it, can fully account for Sedna being at its current location and following its current trajectory. Some of the oldest gravitational perturbations, ones that would have scattered Sedna outward during the chaotic migration period of the early solar system, may not be sufficient to explain the extreme remoteness of Sedna's aphelion. This has led some astronomers to propose that an undiscovered planet, sometimes called Planet 9 or Planet X, might exist in the far outer reaches of the solar system, and that the gravitational influence of this hypothetical body could account for Sedna's orbit and for the orbits of several other distant, unusual objects. However, it is crucial to emphasize that Planet 9 remains entirely hypothetical. No direct observation of such a planet has been made, no telescope has captured an image of it, no spacecraft has detected it. The entire concept of Planet 9 is an inference based on the orbital characteristics of objects like Sedna, a kind of reverse reasoning that says, if these orbits are unusual, then perhaps an unknown body is causing the unusualness. Alternative explanations have been proposed, including perturbations from passing stars in the distant past, and the gravitational effects of a remnant stellar cluster that may have formed with the Sun billions of years ago before dispersing. The truth is that Sedna's origins remain genuinely mysterious, one of the most fascinating unsolved problems in planetary science. What we can say with certainty is that Sedna is extraordinarily distant, extraordinarily remote, and extraordinarily slow in its celestial journey around the Sun. Another dwarf planet candidate, Orcus, represents a different kind of strange world, one whose orbit places it in a particular resonance with Neptune that mirrors the resonance of Pluto itself. Orcus was discovered in 2004 and is named after the Etruscan god of the underworld, continuing the tradition of naming scattered disk objects after mythological underworld deities. With a diameter of approximately 917 kilometers, Orcus is somewhat smaller than Sedna, but still a substantial world, the seventh or eighth largest trans-Neptunian object, depending on current estimates. Orcus possesses a known moon called Vanth, which is large relative to its parent body, making the Orcus system something of a binary pair rather than a primary, with a small satellite. The name Anth comes from Etruscan mythology, the female counterpart and guardian of the underworld. Orcus orbits at an average distance of about 39 astronomical units from the Sun, comparable to Neptune itself, and follows a path that is remarkably similar in many respects to Pluto's orbit. Both objects participate in what is called a 2-to-3 orbital resonance with Neptune, a gravitational relationship in which Pluto orbits twice for every 3 orbits that Neptune completes. This resonance keeps Pluto in a stable orbit despite Neptune's gravitational influence, preventing the larger planet from ejecting the smaller object into interstellar space. Orcus participates in a different resonance, a 1-to-2 resonance which similarly stabilizes its orbit. The spectroscopic properties of Orcus suggest a surface composition, including methane ice and water ice, materials found on many Kuiper belt objects. The reflectivity of Orcus indicates a relatively bright surface, making it visible to powerful telescopes, despite its great distance. The presence of Vanth provides astronomers with a tool to measure Orcus's mass through orbital dynamics, allowing a more precise understanding of this distant world's composition and internal structure. In some ways, Orcus can be thou below light of us, the counterpart or twin of Pluto in the outer solar system, another large object participating in orbital resonances with Neptune, another world of ice and mystery in the deep cold. The concept of orbital resonance is fundamental to understanding why objects in the outer solar system exist where they do and follow the paths they follow. Resonance occurs when one orbiting body completes its orbit in a simple mathematical ratio to another orbiting body. The most famous example involves the moons of Jupiter. Io, Europa, and Ganymede participate in a 1 to 2 to 4 resonance, meaning that while Ganymede completes one orbit, Europa completes 2, and Io completes 4. These objects are locked in an orbital dance, their gravitational interactions balanced in such a way that they maintain these precise ratios. In the outer solar system, resonances also govern the arrangement of objects. The 2 to 3 resonance of Pluto means that Pluto is protected from being scattered by Neptune. Despite orbiting in Neptune's vicinity, objects in the Kuiper belt also participate in various resonances. Resonances that were likely established during the migration of the giant planets in the early solar system. The 2 to 5 resonance, 3 to 7 resonance, and many others appear as gaps or clumps in the distribution of Kuiper belt objects, with higher densities of objects at resonant locations and lower densities in non-resonant regions. These resonances can be thought of as gravitational highways, places where objects naturally cluster because the physics of orbital mechanics favors those locations. Understanding resonances is crucial for understanding the architecture of the solar system and for predicting where yet undiscovered objects might be found. An astronomer searching for a hypothetical new dwarf planet might calculate where resonant orbits would be and focus observations on those regions, knowing that the laws of physics favor the existence of objects in those particular locations. The gravitational locking that resonances create has allowed objects like Pluto and Orcus to survive for billions of years in regions where they might otherwise have been scattered outward or flung inward by the gravitational influence of Neptune. The dwarf planet candidate, Salacia, represents yet another category of distant icy world, and notably, Salacia is known to be in a binary system with another significant object. Salacia itself measures approximately 950 kilometers in diameter, making it a leading candidate for dwarf planet classification. The object is named after the Roman goddess of salt water, a fitting name for an object so far from the warmth of the sun that it exists in perpetual frigidity. Salacia was discovered in 2004 and orbits in the classical Kuiper belt at an average distance of about 42 astronomical units. The companion object in the Salacia system is called Actaea, named after a sea nymph in Greek mythology. The Salacia-Actaea system is notable because the two objects are comparable in size relative to each other, making them something of a true binary pair rather than a clear primary-secondary relationship. Binary objects in the outer solar system are not rare, and several dwarf planets and dwarf planet candidates have satellites ranging from small moons to substantial companion objects. The existence of binary pairs and multiple object systems in the Kuiper belt and scattered disk suggests that formation processes in the outer solar system often produce more than one object. either through collision or fragmentation, or through a primordial formation process that created multiple bodies in the same region of space that never fully coalesced into a single object. The object provisionally designated 2007 or 10, often referred to as 2007 or 10, remains one of the largest known trans-Neptunian objects that has not yet received an official name. This is remarkable and somewhat unusual, as most objects of this size and prominence in the astronomical record have been formally named by the International Astronomical Union. 2007 or 10 measures approximately 1,350 kilometers in diameter, making it one of the largest known dwarf planet candidates, potentially larger than Haumea. It was discovered in 2007 during systematic surveys of the outer solar system, but the process of formal naming has not yet been completed, leaving this substantial world operating under its provisional designation. The fact that one of the largest known dwarf planet candidates remains unnamed speaks to the sometimes slow pace of formal astronomical nomenclature and the vast number of distant objects that continue to await official recognition and study. When 2007 or 10 is eventually named, it will likely receive a name following the International Astronomical Union's conventions for scattered disk objects, probably derived from the mythology of an underworld deity. The object is distinctly red, suggesting a surface composition rich in tholins or other complex organic compounds that have been altered by cosmic radiation and ultraviolet light over billions of years. The orbit of 2007 or 10 is inclined and eccentric, consistent with its classification as a scattered disk object, and it has been observed to have at least one moon, providing opportunities for astronomers to calculate its mass and understand its composition more completely as future observations accumulate. The reddest objects in the solar system are found predominantly in the outer reaches, beyond Neptune, where the cold preserves volatile ices and allows complex chemical reactions to proceed very slowly over billions of years. Gong, with its distinctive crimson hue, is one of the reddest objects known, a coloration that results from the production of tholins, reddish, carbon-rich polymers created when ultraviolet radiation and cosmic rays alter methane, nitrogen, and water ice on the surface. The production of these reddish compounds appears to be a natural consequence of exposure to radiation over vast time periods, a process that accelerates as solar radiation reaches the object more directly during its approach to perihelion. Sedna is also notably red, a coloration that has led some astronomers to propose that Sedna might have a surface composition even richer in organic materials than typical Kuiper Belt objects, with some spectroscopic evidence suggesting the presence of iron oxides and other minerals mixed with the ices. The presence of these reddish, complex organic compounds on distant dwarf planets tells us that chemical complexity exists in the outer solar system, and that the surface chemistry of these worlds is not static, but rather evolves gradually over time through radiation-driven processes that continue even in the extreme cold and darkness of the distant reaches. Other red objects in the outer solar system include various smaller trans-Neptunian objects like 2007 or 10 and some centaurs, which are icy bodies that orbit between Jupiter and Neptune, and are sometimes considered intermediate between Kuiper Belt objects and comets. The exact chemical nature of the red coloration varies from object to object, but the general pattern suggests that organic chemistry, or at least the chemistry of carbon-containing compounds, plays a significant role in the surface evolution of distant icy worlds, with implications for understanding how chemical complexity can persist in some of the coldest places in the solar system. The distinction between the classical Kuiper Belt and the scattered disk is fundamental to understanding the structure and dynamics of the Trans-Neptunian region and the processes that shaped the outer solar system billions of years ago. The classical Kuiper belt consists of objects with relatively low orbital eccentricities and low orbital inclinations, meaning they follow nearly circular paths that lie close to the plane of the solar system in a region of comparative orbital stability. Objects in the classical Kuiper belt have orbital periods typically ranging from 200 to 300 years, and they maintain fairly stable orbits that have changed little since the formation of the solar system, suggesting that these objects have remained in their current locations for the entire orbital areas of the solar system's history. The classical Kuiper belt extends from roughly the orbit of Neptune at about 30 astronomical units out to about 55 astronomical units from the Sun, a region sometimes called the primordial Kuiper belt to distinguish it from its scattered companions. Objects in this region, such as Makemake and most of the smaller Kuiper belt objects, have likely remained in the Kuiper belt throughout the history of the solar system, preserved in a kind of deep freeze where they have changed little since their formation billions of years ago in the solar nebula. The scattered disk, by contrast, contains objects with far more extreme orbital characteristics and dramatic paths through space. Objects in the scattered disk have higher eccentricities, meaning their orbits are more elongated and elliptical, and higher inclinations, meaning they travel on paths that are tilted at steeper angles relative to the solar system's plane, sometimes at angles of 40 or even 50 degrees or more. Many scattered disk objects have orbital periods in excess of 200 years, with some like Sedna having periods of thousands of years or more, reflecting their vast distances from the Sun. The scattered disk objects are generally thought to have been scattered into their current orbits by gravitational interactions with the giant planets, particularly Neptune, during the early chaotic period of the solar system's formation, when planetary migration reshaped the entire outer solar system. Objects such as Eris, Gong and Sedna populate this region, worlds that travel on extreme trajectories as a consequence of ancient gravitational encounters that sent them hurtling outward into the cold darkness. The division between the classical Kuiper belt and the scattered disk is not sharp, but rather a gradual transition, with objects of intermediate characteristics bridging the two populations and making any precise boundary between them somewhat arbitrary. Far beyond even the scattered disk lies a population of objects called detached objects, bodies whose orbits are so extreme that they appear to have been separated from any clear gravitational influence by the known planets. These objects have orbits with very large semi-major axes, meaning their average distance from the Sun is extraordinarily large, and yet they do not approach Neptune closely enough for Neptune's gravity to dominate their motion or to explain their current orbital positions through simple gravitational interactions. The existence of such objects is genuinely puzzling in some respects, and their origins remain a subject of active investigation and considerable scientific debate. The leading explanation involves the passage of nearby stars in the distant past. The Sun and its planetary system did not form in isolation, but rather in a dense stellar cluster containing thousands of stars, a chaotic birthplace of stars where gravitational interactions were commonplace. Over the course of millions of years, gravitational interactions between the Sun and nearby stars would have scattered small bodies in the outer solar system, sending some inward and others outward to enormous distances at speeds that would carry them far beyond the reaches of the planets. Most of the stars eventually dispersed, moving away to different regions of the galaxy, but the evidence of their gravitational influence persists in the orbits of the scattered and detached objects they left behind, as proof of the violent early history of the solar neighborhood. Another possibility involves the long-range gravitational influence of the Oort cloud, a hypothetical spherical shell of icy objects surrounding the solar system at distances of thousands to hundreds of thousands of astronomical units from the Sun. The Oort is thought to be the source of long-period comets, objects that occasionally fall inward towards the inner solar system, where we observe them as dramatic celestial visitors streaking across the night sky. The presence of detached objects with extreme orbits demonstrates that the solar system extends far beyond the familiar planets and even beyond the Kuiper belt, into regions of profound darkness and cold, where objects orbit in paths so elongated and so distant that they require thousands of years or more to complete a single revolution around the Sun. The question of whether an undiscovered planet orbits in the far reaches of the solar system beyond even these extreme objects remains one of the most tantalizing mysteries in modern astronomy. The proposal, sometimes called Planet 9 or Planet X, arose from observations that seemed inconsistent with known gravitational interactions. When astronomers calculated the orbits of distant scattered disk objects, they found clustering and alignment patterns that would be unlikely to occur by chance. If all the objects had been scattered randomly by Neptune's gravity during the early solar system, they should distribute more evenly throughout the outer regions. Instead, their orbits showed a suspicious tendency to align in certain ways, suggesting the possible influence of an unseen massive body. The hypothetical planet would orbit at an average distance of perhaps 400 to 800 astronomical units from the Sun, making it far more distant than Pluto or Eris. Such an object would receive so little sunlight that its surface would exist in perpetual darkness colder than any other place in the solar system. If Planet 9 exists, it would be smaller than Earth, but far more massive than any known dwarf planet, a world that has escaped detection for billions of years through sheer distance and darkness. However, it is crucial to emphasize that no direct evidence confirms this hypothesis. No telescope has imaged such a planet. No spacecraft has detected it. No spectrum has been obtained from any such object. The evidence remains entirely circumstantial and inferential. Alternative explanations have been proposed, including the possibility that the orbital clustering could result from observational bias, meaning that astronomers simply find objects more easily at certain orbital angles. Another possibility involves perturbations from passing stars in the distant past that might have scrambled the outer solar system's structure in ways that account for the observed alignments without requiring an undiscovered planet. The mystery persists because the solar system continues to reveal complexities that challenge our understanding, and the possibility of an unknown world lurking in the darkness remains genuinely open, neither confirmed nor ruled out by available evidence. Cryovolcanism, or volcanic activity involving eruptions of ice and frozen materials rather than molten rock, represents one of the most intriguing possibilities for ongoing geological processes on distant dwarf worlds. On planets and moons closer to the Sun, volcanism occurs when internal heat causes rock to melt and erupt as lava flows and ash. In the outer solar system, where surface temperatures remain far below the freezing point of water, volcanoes would function quite differently. Instead of molten rock, cryovolcanoes would erupt mixtures of water ice, methane ice, ammonia ice, and various other frozen compounds, possibly mixed with darker material from the interior. These eruptions would be slow compared to volcanic activity on Earth, with semi-solid slurries pushing through cracks in the surface rather than explosive bursts. New Horizons observations of Pluto revealed features called Wright Munns and Pickard Munns that may represent cryovolcanic structures, with evidence suggesting that past eruptions deposited materials with a consistency similar to toothpaste across portions of the surface. On Haumea, the rapid rotation and collisional history raise the possibility that internal heat generated by tidal friction or the decay of radioactive elements might drive small-scale cryovolcanic activity, though direct evidence remains elusive. The presence of different types of ices on a dwarf planet's surface tells astronomers something about the thermal history of that world. If surface materials show signs of crystalline rather than amorphous structure, the implied thermal activity might indicate cryovolcanism or other heat generation processes. However, establishing that activity is currently occurring remains extremely difficult from great distances. A cryovolcanic plume venting methane gas into space would dissipate quickly and escape detection by all but the most sensitive instruments pointed at exactly the right location, at exactly the right moment. The uncertainty surrounding present-day cryovolcanism on these worlds makes it a subject of intense scientific speculation, with careful observers and theorists working to distinguish between evidence of past activity, ongoing processes, and the possibility that any apparent thermal anomalies could result from other explanations, such as ring systems or dust. The ices that dominate the surfaces and interiors of trans-Neptunian objects create a chemistry fundamentally different from the rocky terrestrial planets orbiting closer to the Sun. Methane ice, frozen at temperatures around 60 to 70 Kelvin under certain pressures, appears as a reddish-brown surface coating on Makemake and other objects in the outer solar system, colored by the production of complex organic compounds when ultraviolet radiation alters the methane over billions of years. Nitrogen ice becomes solid at temperatures below 63 Kelvin and appears white or pale grey, coating surfaces where the temperature never rises enough to allow this material to remain gaseous. The heart of Pluto, Sputnik Planitia, contains layers of nitrogen ice interspersed with methane and carbon monoxide ice, creating a geological and chemical complexity that surprised astronomers who had expected a uniform icy surface. Water ice in the outer solar system exists not as the familiar ice of Earth's glaciers, but often in exotic forms, including crystalline structures that reveal something about the thermal history of each world. Ammonia ice forms at even colder temperatures and may exist in the interiors of some dwarf planets, where internal pressure prevents it from vaporizing even at the low temperatures of the outer solar system. The presence of these various ices tells a story about the chemical composition of the solar nebula billions of years ago, the mixture of volatile materials that existed in the region where these worlds formed. As measurements become more precise and spectroscopic observations reveal subtle changes in the distribution of different ices on surfaces, astronomers gain insight into processes that may be ongoing even now, from the gentle sublimation of surface materials, as orbits bring these worlds slightly closer to the Sun, to the possible interaction of different ices that might trigger chemical changes when they come into contact. The brightness of a distant dwarf planet, as observed from Earth, tells astronomers something about the amount of sunlight it reflects, a property called albedo, or reflectivity. Eris shines with an extremely high albedo, reflecting about 96% of the light that reaches it, comparable to freshly fallen snow on Earth. This high reflectivity results from the methane nitrogen ice that coats its surface, materials that absorb very little visible light. Makemake has a lower albedo, appearing darker than Eris, but still relatively bright by the standards of distant objects, suggesting a surface with some darker materials mixed among the ices. Gong, with its distinctive reddish coloration, has an albedo modified by the tholins and other complex organic materials that cover its surface, absorbing some wavelengths of light preferentially. The albedo of an object matters crucially for calculating its actual diameter. When astronomers observe a distant object and measure how bright it appears, they must determine how much of that brightness results from the object's size and how much results from its reflectivity. A small, highly reflective object can appear as bright as a larger, darker object. Without knowing the true reflectivity, astronomers cannot accurately determine the true size. This is why multiple observational techniques are necessary. Thermal infrared observations, where astronomers measure the heat radiation emitted by these worlds, can help constrain the albedo because they depend on the object's temperature and size rather than its reflectivity. Stellar occultations, where these objects pass in front of distant stars and briefly block the starlight, provide direct geometric information about size and shape. By combining multiple types of observations, astronomers can gradually build a more accurate picture of each world's true physical characteristics. The thermal emissions from these distant dwarf planets tell astronomers about their surface temperatures and something about their interior thermal structure. Objects so far from the Sun receive very little direct heating from solar radiation. Pluto, orbiting at an average distance of about 40 astronomical units, receives only about 1,700 times less solar energy per square meter than Earth does. Yet spectroscopic observations and thermal measurements reveal that Pluto's surface reaches temperatures down to about 38 Kelvin in some regions, far colder than the temperature of direct solar heating alone would suggest. This implies that the surface at different locations has different properties, with some regions more efficient at retaining heat or more exposed to what little warmth does reach them. Eris, at even greater distances, experiences even less solar heating, yet New Horizons data, combined with thermal observations, suggests surface temperatures potentially as low as 30 Kelvin. The interior of these worlds, warmed by the decay of radioactive elements like uranium and thorium, may be somewhat warmer than the surface, despite the extreme cold. Heat flowing from the I-5 interior through the thin crust creates temperature gradients that influence which materials can exist in solid form. Water ice behaves differently at slightly different temperatures, and ammonia-water mixtures create strange eutectics, points where materials melt at temperatures lower than either pure substance would melt alone. The thermal structure of a dwarf planet's interior influences what processes might occur, whether cryovolcanism remains possible, and whether subsurface oceans of liquid water might persist beneath frozen crusts. Measuring thermal emissions requires sensitive infrared detectors, mounted on space telescopes, or pointed at the sky, from Earth's surface, with sophisticated techniques to account for atmospheric absorption. The data arrives as faint thermal signatures that must be carefully distinguished from background radiation and instrumental noise, making each measurement a triumph of observational astronomy. The discovery of distant dwarf planets relies on fundamental observational techniques that have remained essentially similar since the earliest telescopic observations of the solar system, adapted and refined through technological advances. Astronomers searching for new objects begin with repeated imaging of the same regions of sky, taken nights or weeks apart. If an object is moving, its position will shift slightly from image to image as it orbits the Sun. The background stars remain fixed, appearing in the same positions in repeated images, but a moving object appears in different locations. Detecting this slow motion against the background of stars is the first step in discovery. Modern surveys use vast CCD detectors attached to telescopes, instruments capable of capturing images of millions of pixels, showing tiny portions of the sky in exquisite detail. Computers automatically search these images for moving objects, comparing positions in successive images to identify things that have shifted location. However, the automatic search software must be tuned carefully to avoid false positives from cosmic rays, image artifacts, and other noise. The example of Eris's discovery illustrates this perfectly. The initial observations in 2003 captured Eris on film, but the automatic search software excluded it because it was moving so slowly that the search parameters filtered it out. Not until the team reanalyzed the data in 2004 with adjusted search parameters did they recognize that they had been looking at Eris all along. Once a moving object is detected, astronomers observe it repeatedly over weeks and months to determine its orbital path. The position at different times allows calculation of the object's orbital elements, determining where it will be in the future and confirming whether it is truly a new discovery rather than a known object. Spectroscopic observations reveal the composition of the surface through the light reflected by and emitted from the object. Colors and spectral features tell astronomers whether they are looking at water ice, methane ice, or other materials. The brightness combined with spectroscopic data helps astronomers estimate the object's size, though this remains uncertain without additional information. The challenges of observing objects in the outer solar system grow more severe with distance, creating obstacles that make even basic measurements uncertain and time-consuming. These worlds orbit so far from the Sun that they receive virtually no sunlight compared to objects closer to the solar system. Even the brightest dwarf planets beyond Pluto remain faint by astronomical standards, visible only through powerful telescopes, and many candidate dwarf planets are so dim that detecting them requires telescopes among the largest on Earth or in space. The motion of these objects across the sky is so slow that measuring it requires months or years of observations rather than days or weeks. An object near the Kuiper belt might move only a tiny fraction of an arcsecond across the sky each night, a distance so small that it is invisible to the human eye through any telescope. Only electronic detection and careful measurement can establish this motion. The extreme distance also means that determining the size of an object becomes extremely difficult. Without a spacecraft actually reaching these worlds and measuring their size directly, astronomers must rely on indirect methods. The brightness combined with albedo estimates provides one approach, but albedo is not directly measurable for distant objects, making the size calculation uncertain. Thermal measurements offer another approach, but they depend on assumptions about the object's thermal properties and internal heat. Even the best observations leave uncertainties of perhaps 30 or 40% in the diameter estimates of dwarf planets, and for smaller or more distant candidates, the uncertainties are even greater. The faintness of these objects also means that obtaining spectroscopic observations requires extensive integration time on the largest telescopes. Hours of observation might be needed to accumulate enough light to create a reliable spectrum. This makes comprehensive spectroscopic surveys of all known dwarf planet candidates impractical with current technology, leaving many objects unobserved in wavelengths that would reveal their composition. The extreme cold and distance also means that these objects cannot be visited by robots without expending enormous resources and accepting a mission timeline spanning years or decades. Brightness changes, observed in light curves of distant dwarf planets, reveal information about rotation. An object rotating and reflecting sunlight from a non-uniform surface will appear brighter and dimmer as different regions rotate into and out of view. If one hemisphere is darker than the other, for example, the brightness will vary in a pattern corresponding to the object's rotation period. By observing the brightness over hours and measuring the time between brightness maxima, astronomers can determine how long each rotation takes. Haumea's dramatic rotation period of just under 4 hours was established through this technique, confirming that this world rotates far faster than most objects in the solar system. The brightness variations also hint that Haumea's surface is non-uniform, consistent with its elongated shape. Different sides of the ellipsoidal world reflect different amounts of light as they rotate into view. For objects with more uniform surfaces or orientations that happen to point poles toward Earth, detecting rotation through brightness variations becomes difficult or impossible. Some dwarf planets may rotate slowly enough that brightness changes occur over many hours, requiring extended observation to detect. Others might rotate such that their poles point toward Earth, eliminating the brightness variations that rotation normally produces. These limitations mean that determining rotation periods remains difficult for many distant objects. The rotation period, combined with the object's size, can be used to calculate how much centripetal acceleration the rotation produces at the equator. For rapidly rotating objects, like Haumea, this centripetal acceleration contributes to the object's elongated shape, and comparing the rotation rate to the observed shape helps astronomers understand the object's internal rigidity and composition. The Hubble Space Telescope, orbiting Earth above the distorting effects of the atmosphere, has provided some of the highest resolution observations of distant dwarf planets and dwarf planet candidates. Hubble's Wide Field camera can detect extremely faint objects because it combines a large mirror with sensitive electronic detectors and the advantage of observing from space without atmospheric turbulence. Many dwarf planets visible from the ground only as point sources of light appear in Hubble images still unresolved, meaning they are so small or distant that Hubble cannot show them as extended disks. However, Hubble can image them as bright points against background stars with sufficient precision to measure their positions very accurately. Multiple Hubble observations taken years apart allow the determination of proper motion across the sky, and combining positional measurements from different telescopes and different years allows precise calculation of orbital parameters. Hubble observations have been crucial in confirming that faint moving objects discovered in survey data are genuinely distant trans-Neptunian objects rather than asteroids in the inner solar system. The archive of Hubble images taken over more than 3 decades provides a rich database of observations that astronomers continue to analyze, sometimes discovering new information in data that is years or decades old. For some dwarf planets, Hubble obtained detailed observations during specific viewing opportunities, when the objects happened to be in particularly accessible regions of the sky. These observations have been used to study the moons of dwarf planets, to detect the subtle light reflection variations from rotating non-spherical bodies, and to confirm the presence of moons or ring systems. However, Hubble's observations of the most distant objects are limited by the simple fact that even a space telescope cannot overcome the challenge of extreme distance combined with faintness. Many dwarf planet candidates remain beneath Hubble's detection threshold or require multiple orbits of expensive observation time to achieve useful signal-to-noise ratios. The newest space telescope, the James Webb Space Telescope, offers improved sensitivity, particularly in infrared wavelengths, opening new possibilities for observing these distant cold worlds through measurements of their thermal emissions. The Atacama Large Millimeter, Submillimeter Array, a facility of radio telescopes in the high mountains of northern Chile, has made remarkable contributions to the study of distant dwarf planets through observations of their thermal radiation. ALMA observes at wavelengths in the millimeter and submillimeter range, detecting radiation that is primarily thermal in origin rather than reflected sunlight. This technique is particularly powerful for distant objects that are very faint in visible light but emit measurable amounts of thermal radiation. Haumea observations have helped constrain the sizes and albedos of dwarf planets by measuring how much thermal radiation they emit at known distances from the Sun. An object with a higher albedo reflects more sunlight and absorbs less, so it should be cooler and emit less thermal radiation for a given size. By combining measurements of reflected light with measurements of thermal emission, astronomers can solve for both the albedo and the size simultaneously, reducing the ambiguity that plagues observations using only one technique. Haumea's high angular resolution also allows detection of close companions and studies of the geometry of ring systems. The rings of Quasar were detected partly through Haumea observations, complementing stellar occultation data. The array's sensitivity to faint sources means that observations of the largest dwarf planets are now routine, while observations of smaller candidates push against the limits of current sensitivity. Haumea operates as an interferometer, combining signals from many separate dishes to create the equivalent of a much larger telescope. This technique provides angular resolution far superior to what any single dish could achieve, making Haumea one of the most powerful facilities for observing faint solar system objects that appear very small and faint from Earth's perspective. Stellar occultations represent one of the most powerful techniques for learning about the sizes and shapes of distant dwarf planets. When a dwarf planet passes in front of a distant star as viewed from Earth, the planet briefly blocks the starlight, causing the star's brightness to drop. If observers at many locations along the path of the occultation time exactly when the star disappears and reappears, the precise timing at different geographic locations allows reconstruction of the object's size and shape with remarkable accuracy. The edges of the dwarf planet block the star at slightly different times depending on where the observer is located, and by mapping out these times precisely, astronomers can construct a detailed silhouette of the object. This technique is particularly valuable because it depends on geometry rather than on assumptions about the object's reflectivity or thermal properties. Stellar occultations have revealed that some dwarf planets are not spherical but flattened or even elongated. Haumea's triaxial shape was confirmed through occultation data from multiple sites. The rings of Quasar were discovered through the detailed analysis of occultation light curves, which showed subtle variations indicating the presence of material extending outward from the primary body. Organizing a successful occultation observation requires international coordination because the path across the Earth where the occultation is visible extends only over a narrow band, perhaps hundreds of kilometers wide and thousands of kilometers long. Astronomers must arrange for telescopes at multiple sites along this path to observe simultaneously. Predicting exactly where the occultation path will cross requires precise knowledge of the observer's location, the position of the star, and the orbit of the dwarf planet, with errors accumulating over time as orbits become less certain for more distant objects. Recent occultations have been observed from space using the Gaia satellite, which continuously monitors millions of stars and can detect the brief dips in brightness caused by occultations without being affected by Earth's atmosphere or the observer's location on the ground. Determining the actual size of a dwarf planet without direct measurement from spacecraft represents a complex problem in observational astronomy, one where different techniques give different results, and the true answer often remains uncertain. The brightness of an object as viewed from Earth depends on 4 factors: the distance to the object, the amount of sunlight reflected, the object's reflectivity or albedo, and its actual physical size. If an observer knows all 4 of these factors, the 5th can be calculated. However, astronomers typically know only the distance and the brightness, making the size calculation ambiguous. Thermal observations help break this degeneracy, because an object's thermal emission depends on its size and its surface temperature, but is relatively independent of its reflectivity. However, surface temperature depends on factors including the object's albedo, its orbital position, and its internal heat production. Introducing additional unknowns. By combining observations across multiple wavelengths and using careful modeling, astronomers can narrow the possibilities and estimate both the albedo and the size. However, uncertainties often remain, particularly for objects that are smaller or more distant than the well-studied dwarf planets. For objects with known moons, measuring the moon's orbit provides information about the primary body's mass. If the mass and the size can both be estimated, the density follows, and density can help constrain the composition and internal structure. However, this approach requires that an object actually possess a moon, which not all dwarf planets, or candidates do. The uncertainty in size estimates has practical consequences. If a dwarf planet's size is estimated to be uncertain by 30%, then the possible range of sizes spans from about 70% to 130% of the estimated value. This translates to uncertainties in volume even larger, since volume scales with the cube of the radius. These size uncertainties propagate into calculations of surface area, gravitational acceleration, rotation dynamics, and many other physical properties. The formation of dwarf planets in the outer solar system remains one of the great unsolved problems in planetary science, a puzzle that astronomers approach through a combination of direct observations, theoretical modeling, and comparisons with the processes that formed the inner solar system. In the leading formation model, the solar nebula in the region beyond the giant planets contained numerous icy planetesimals, bodies ranging from kilometers to tens of kilometers across. These planetesimals gradually accumulated through collisions, growing larger and capturing additional material through their enhanced gravity. The largest objects, reaching sizes of perhaps 100 kilometers or larger, could grow rapidly through the gravitational focusing of passing planetesimals. However, the process of planetary growth depends on the initial population of planetesimals and on their orbital dynamics. If planetesimals are too widely spaced, they will rarely collide and growth becomes slow. If they are closely packed, collisions happen frequently, but often result in fragmentation rather than gentle accumulation. The optimal conditions for planet formation exist in a relatively narrow range of planetesimal densities and orbital velocities. The solar system, it appears, fell within this range in certain regions but not others, explaining why planets formed successfully in some regions but not in the asteroid belt between Mars and Jupiter, where Jupiter's gravity prevents large bodies from accumulating. In the outer solar system, the process of planetary growth appears to have created many objects in the range of hundreds to thousands of kilometers across, bodies that would eventually become dwarf planets and dwarf planet candidates. However, the exact size distribution of these objects and the timing of their formation remain incompletely understood. Planetesimal accretion, the gradual growth of bodies through collisions and gravitational accumulation, provides the foundation for understanding how dwarf planets grew from smaller seed objects. In the early stages, planetesimals are numerous and small, perhaps a few kilometers across. Each collision between planetesimals releases energy that could be detected as a heat signature if it occurred on Earth. But in the cold outer solar system, this energy radiates to space and the bodies remain at very low temperatures. As planetesimals accumulate, the largest objects grow faster because their enhanced gravity reaches farther and concentrates material more efficiently. The growth process accelerates until a few dominant bodies emerge, each of which continues to accumulate smaller planetesimals, 6 in its vicinity. However, as the largest bodies grow, gravitational scattering of planetesimals becomes important. Bodies passing near a large proto-dwarf planet may be accelerated or decelerated, either ejected into the outer reaches of the solar system or sent inward toward the inner solar system. This process gradually empties the region of smaller planetesimals, slowing the accretion of the largest bodies. The end result is that accretion halts before all available planetesimals have been incorporated into the largest objects. The remaining planetesimals either get ejected or remain as a population of smaller bodies orbiting around and among the larger objects. This explains why the present-day solar system contains not one or two giant bodies in each orbital region, but rather many before population of smaller bodies orbiting around and among the larger objects. This explains why the present-day solar system contains not one or two giant bodies in each orbital region, but rather many bodies of varying sizes. The timescale for planetesimal accretion in the outer solar system remains uncertain, with estimates ranging from hundreds of thousands of years to perhaps a few million years for the growth of kilometer-sized bodies up to dwarf planet dimensions. The NICE model, named after the French city where it was developed, proposes a radical rearrangement of the outer solar system in the early stages of its evolution. According to this model, the giant planets Jupiter, Saturn, Uranus, and Neptune initially formed in a more compact configuration at smaller distances from the Sun than they now occupy. The early solar system contained a dense disk of planetesimals extending outward from the giant planets. Gravitational interactions between the giant planets and planetesimals, combined with interactions among the planets themselves, caused the planets to migrate outward. Jupiter and Saturn eventually moved outward to their present positions, while Uranus and Neptune moved even farther out. This migration stirred the primordial planetesimal disk, dramatically scattering most of the planetesimals, either outward to form the Oort cloud or inward toward the inner solar system, where they left evidence of late heavy bombardment recorded in the lunar crater record. The NICE model explains several features of the present-day solar system. The near-resonant orbital relationships of some objects with Neptune, such as Pluto's 2 to 3 resonance, could result from capture into these resonances by Neptune as it migrated outward. The division between the classical Kuiper belt and the scattered disk, with their different dynamical characteristics and orbital distributions, could result from the violent scattering that occurred as Neptune moved outward. The existence of detached objects with extreme orbits could result from gravitational encounters with the migrating giant planets. However, the NICE model remains controversial and incompletely proven. Different simulations of the model produce somewhat different results depending on the assumptions about initial conditions. Some simulations suggest that the migration events occurred relatively recently in the solar system's history, perhaps only within the first few 100 million years, while others suggest longer timescales. The observational evidence that could definitively prove or disprove key predictions of the NICE model remains ambiguous or incomplete, leaving the model as one of several competing hypotheses about the early solar system's history. The survival of some objects intact through billions of years of solar system evolution, while others were fragmented, scattered, or destroyed, remains a puzzle with implications for understanding the present-day distribution of dwarf planets. Some dwarf planets and candidates appear to be relatively pristine remnants from the early solar system, bodies that have remained in stable orbits far from perturbing influences. Pluto's location in orbital resonance with Neptune likely protected it from being ejected by the migrating giant planets. The members of the classical Kuiper belt, with their relatively circular and aligned orbits, may represent objects that were never significantly scattered and have remained in the region where they formed. Other objects, however, show evidence of dramatic histories. Haumea's distinctive shape, rings, moons, and the association of many other objects with its collisional family suggest that Haumea experienced an enormous impact that fragmented or restructured the body and ejected debris that eventually became the other objects in the family. Eris's highly inclined and eccentric scattered disk orbit suggests a history of dramatic gravitational scattering that sent it to its current location. The existence of detached objects like Sedna implies encounters with other massive bodies or gravitational perturbations that ejected these worlds into extreme orbits. The survival of the dwarf planets we observe today may depend on subtle historical accidents. An object located slightly farther out or slightly closer to a gas giant might have experienced a different gravitational encounter and followed a different evolutionary path. The dwarf planets that survived may not represent the entire population that existed in the early solar system. Many bodies might have been ejected entirely, either toward the inner solar system, where they coevolution entire, but dwarf planets that survived may not represent the entire population that existed in the early solar system. Many bodies might have been ejected entirely, either toward the inner solar system, where they collided with planets and moons, or outward into the Oort cloud, where they remain unobserved, billions of kilometers from Earth. The fact that we observe certain dwarf planets and candidates may reflect not just their physical properties, but also the fortunate accidents of gravitational dynamics that allowed them to survive in detectable orbits. Groups of smaller objects orbiting the Sun near the major dwarf planets often bear the marks of shared origins, bodies born from the same collisional event or dynamical process billions of years ago. The Haumea collisional family represents the most dramatic example of this connection. Haumea itself displays the scars of an ancient impact so violent that it restructured the entire body, spinning it up to its present rapid rotation and elongating its shape through the effects of centrifugal force. The collision scattered debris outward, and fragments large enough to remain gravitationally bound to the region eventually coalesced into smaller bodies, including Haumea's moons, Hi'iaka and Naumaka, both of which may have formed from the collision-generated debris. Other members of the family, smaller trans-Neptunian objects with similar orbital characteristics and spectroscopic properties, likely formed from the same impact event. The discovery of these family relationships provides astronomers with a way to understand the collision history of the outer solar system, using the present distribution and composition of objects to reconstruct events that occurred in the distant past. Haumea's family spans a range of sizes and orbital configurations, but members share certain spectroscopic signatures, indicating that they formed from the same parent body and retain surface compositions modified by the collision and billions of years of cosmic weathering. The largest family members have themselves experienced subsequent collisions, creating subfamilies and further fragmenting the debris field. Identifying collisional families requires careful analysis of orbital parameters, comparing dozens or even hundreds of objects to find those whose orbital elements cluster together in ways suggesting a common origin. The uncertainties in orbital measurements mean that some objects classified together may not actually share a family relationship, while other actual family members mean that some objects classified together may not actually share a family relationship, while other actual family members might remain unrecognized because orbital measurements lack sufficient precision. These collisional families remind us that the present-day dwarf planets are not static, unchanging bodies, but rather the current survivors of a dynamic history filled with impacts and gravitational interactions that continue to reshape the outer solar system across the vast timescales of planetary evolution. The possibility that these distant dwarf worlds might harbor thin atmospheres represents one of the most exciting frontiers in outer solar system science. As dwarf planets orbit closer to the Sun at certain points in their eccentric orbits, they receive slightly more solar heating. If this heating is sufficient to warm volatile ices on the surface above their sublimation temperatures, those ices will transform directly from solid to gas, creating transient atmospheres that exist only near perihelion, the point of closest approach. Pluto, despite its extreme distance, possesses a thin nitrogen atmosphere that astronomers detected through New Horizons instruments. The atmosphere extends to surprising altitudes and contains layers of haze, suggesting complex atmospheric dynamics, even at temperatures of only 38 Kelvin. The presence of haze layers indicates that atmospheric particles interact with ultraviolet light from the Sun, creating chemical reactions that produce aerosols visible as haze above the surface. Eris may develop a similarly thin atmosphere when it approaches its perihelion in the coming decades, though no atmosphere has been directly detected around this world yet. The calculation of when Eris will reach its perihelion remains important for planning future observations. The James Webb Space Telescope has recently detected gaseous methane above Haumea, making it only the second trans-Neptunian object known to show atmospheric gases. This detection suggests that surface methane is warming enough to sublimate into the gas phase, creating a thin layer of atmosphere above the surface. The detection of atmospheric methane also raised intriguing questions about whether cryovolcanic activity or other unexpected heating mechanisms might be keeping certain regions warm enough to sustain this gaseous phase. Determining whether these atmospheres are transient, existing only near perihelion, and freezing out again as orbits carry the worlds further from the Sun, requires patience and repeated observations over years and decades. Some dwarf planets and candidates may have atmospheres too thin to detect with current telescopes, while others may have lost their volatile inventories to solar heating and escaped to space long ago. The difference between detecting an atmosphere and confirming seasonal variation requires long-term monitoring over decades, observations that often outlast funding cycles and scientific careers. The orbital paths of the most distant dwarf planets carry them through the heavens on journeys that take centuries to complete. And over the course of these vast timescales, the amount of solar heating these worlds receive changes dramatically. Haumea, traveling through an orbit that brings it between about 30 and 47 astronomical units from the Sun, receives more solar energy when near perihelion than when at aphelion. Though the difference in absolute energy is tiny by the standards of planets closer to the Sun, it may be sufficient to affect surface temperatures by tens of degrees Kelvin. Pluto's orbit varies from about 30 to nearly 50 astronomical units, creating substantial seasonal changes over its 248-year orbital period. The presence of various volatile ices on the surfaces of these worlds means that seasonal variations in solar heating will cause these ices to move between solid and gaseous phases in response to orbital position. During the decades when a dwarf planet approaches perihelion, methane ice may sublime away from equatorial regions, only to refreeze at the poles as material escapes toward colder regions. Successive passages near perihelion gradually redistribute the volatile inventory of a dwarf planet's surface, with the most easily sublimated materials concentrated toward the poles and the most stable materials persisting in the sunlit equatorial regions. Models of volatile migration suggest that over millions of years, these processes can substantially alter the distribution of surface materials. Observing these changes requires monitoring the same objects repeatedly over decades, detecting subtle shifts in spectroscopic properties or changes in overall brightness that might indicate surface composition changes. Some dwarf planets discovered only recently will not approach perihelion for centuries or thousands of years, meaning astronomers cannot directly observe how their surfaces change in response to seasonal heating during present-day observations. The possibility that dwarf planets harboring subsurface oceans of liquid water may be far more common than previously suspected emerged from the unexpected findings of the New Horizons mission to Pluto. The presence of a large basin on Pluto's surface, combined with evidence of relatively young surface features and possible cryovolcanism, suggested that significant internal heat persists within this distant world, even at extreme distance from the Sun. If such internal heat exists, it could be sufficient to keep water ice in a softened or even partially melted state in the interior, creating a subsurface ocean. The mechanism generating this internal heat remains unclear because radioactive decay alone cannot produce sufficient warming to maintain a liquid water ocean against the extreme cold at Pluto's surface. Tidal heating from gravitational interactions with Charon, Pluto's large moon, may contribute warmth, though Pluto and Charon are so far from any external perturbing body that sustained tidal heating seems unlikely by conventional calculations. The possibility of a subsurface ocean on Pluto raises profound questions about other dwarf planets. If Pluto, one of the smallest dwarf planets, possesses enough internal heat to maintain liquid water, might larger dwarf planets like Eris and Haumea also harbor subsurface oceans? The energy budget required to keep water liquid depends on the object's size, composition, internal heat production, and surface temperature. Larger bodies retain internal heat longer because their greater mass means greater radioactive element content and slower cooling rates. However, larger bodies also have greater surface area through which to radiate heat into space, creating a competing effect. The balance between internal heat production and surface cooling varies for each object, making each dwarf planet a unique case requiring careful analysis. No direct evidence currently confirms the existence of subsurface oceans on dwarf planets beyond Pluto, but the possibility cannot be ruled out based on available observations. If dwarf planets do harbor subsurface oceans, the implications for habitability and the distribution of potentially habitable environments in the solar system would be profound. Cosmic radiation and solar ultraviolet light bathe the surfaces of dwarf planets in energetic radiation that continuously alters the composition of ice and organic materials. Unlike worlds protected by thick atmospheres, the ices coating these distant bodies receive full exposure to the stellar radiation environment. Ultraviolet photons possess enough energy to break chemical bonds in methane, water, and other molecules, triggering reactions that create new compounds. Over billions of years, these radiation-driven chemical transformations accumulate, gradually darkening the surface and creating complex organic polymers collectively called tholins. The reddish coloration of Gong and other dwarf planets likely results from the accumulation of these complex organic compounds produced by ultraviolet processing of simpler ices. The rate of radiation processing depends on factors including the object's distance from the Sun, its orbital inclination, and the nature of cosmic ray exposure. Objects at high orbital inclinations receive more galactic cosmic rays because their orbits carry them out of the plane where Jupiter's magnetic field provides some protection against these high-energy particles. The radiation environment also varies in time as the Sun's activity and the solar wind change across multi-year cycles, sometimes dramatically intensifying the flux of energetic particles reaching the outer solar system. Measuring the spectroscopic properties of dwarf planet surfaces can reveal the extent of radiation processing, with very dark surfaces indicating ancient, heavily processed materials, and brighter surfaces suggesting either young material or exposure to less radiation. Some regions of a dwarf planet's surface may be fresher than others because impacts excavate material from the interior, exposing unirradiated ice that then begins accumulating radiation damage anew. The interplay between surface radiation processing and potential cryovolcanic activity that delivers fresh material from the interior creates a dynamic surface chemistry that continues to evolve across planetary timescales. The composition of the subsurface may differ significantly from the surface because radiation does not penetrate deeply into the ice. The organic chemistry detected on dwarf planet surfaces through spectroscopic observations reveals a richness of carbon-containing compounds that far exceeds the simple expectation of pure ices. When astronomers obtain spectra of these distant worlds, they detect absorption features consistent with water ice, methane ice, and nitrogen ice, but they also find evidence of more complex molecules. Tholins, polymeric organic compounds produced by ultraviolet radiation and cosmic rays acting on simpler molecules, appear to coat many dwarf planets, imparting the reddish hues observed in telescope images. Other spectroscopic features hint at the presence of alcohols, aldehydes, ketones, and other organic functional groups. The precise identification of these compounds remains uncertain because most have never been directly sampled from distant worlds, and reproducing their spectroscopic signatures requires careful laboratory work. The formation of these organic compounds in the cold outer solar system demonstrates that organic chemistry is not restricted to warm, life-bearing environments, but occurs throughout the solar system wherever ultraviolet radiation and cosmic rays can act on chemical precursors. The presence of diverse organic materials on dwarf planets raises intriguing questions about the chemical heritage of the early solar system. If dwarf planets retain these organic compounds from the primordial nebula, or if they are continuously produced by radiation processing, they may represent samples of the chemical environment from which planets formed. Scientists have suggested that some of the complex organic compounds found on dwarf planets may have contributed to the organic inventory of Earth and other inner planets during the heavy bombardment period, when collisions with distant bodies were far more frequent than in the present era. The correlation between the colors of dwarf planets and their orbital characteristics provides clues about their origins and evolutionary histories. Some dwarf planets display relatively uniform colors across their surfaces, suggesting that their compositions have remained stable over billions of years. Others show color variations that may relate to different surface regions or different compositions in different regions. The colors of objects in the scattered disk tend toward the redder wavelengths, likely because radiation processing has had more time to alter these ancient surfaces. Objects in the classical Kuiper belt often appear somewhat redder than the brightest dwarf planets like Makemake, which displays a notably neutral grey coloration. The reasons for these correlations remain incompletely understood, but likely involve factors including the age of surface materials, the intensity of radiation processing, the types of organic compounds present, and possibly mixing of materials from different sources. Some astronomers have proposed that objects with moderate inclinations may be less heavily processed by cosmic radiation than high-inclination objects, potentially explaining correlations between orbital geometry and surface color. Others suggest that objects injected into the scattered disk more recently may retain brighter surface materials that have undergone less radiation processing than materials on older scattered disk objects. The James Webb Space Telescope, with its unprecedented infrared sensitivity, offers new possibilities for detecting subtle color variations and mapping compositional distributions on dwarf planet surfaces with higher precision than ground-based telescopes can achieve. The extreme distances of dwarf planets beyond Pluto make them extraordinarily challenging destinations for space exploration. obstacles that have prevented the dispatch of any spacecraft to these worlds. The distances are almost incomprehensibly vast by human standards. Pluto orbits at an average of about 40 astronomical units, meaning the light of the Sun takes about 5 hours to reach it. Eris, at an average distance of 96 astronomical units, receives sunlight that departed Earth when a person was sleeping or eating breakfast. To reach these worlds, a spacecraft must overcome the Sun's gravitational pull and travel outward against the seeming emptiness of space. The energy required to propel a spacecraft at the velocities necessary to traverse these distances represents an enormous engineering challenge. A spacecraft must be boosted to nearly 70 kilometers per second relative to Earth to have a reasonable chance of reaching the outer solar system in a human lifetime. Even at these extraordinary speeds, a spacecraft requires years of travel time to reach distant destinations. The New Horizons spacecraft, one of the fastest objects ever launched from Earth, took 9 years to reach Pluto after passing through the solar system. Spacecraft traveling to more distant dwarf planets would require either faster launched from Earth, took 9 years to reach Pluto after passing through the solar system. Spacecraft traveling to more distant dwarf planets would require either faster launched from Earth, took 9 years to reach Pluto after passing through the solar system. Charge velocities, which current rocket technology cannot yet provide, or multi-decade journeys lasting 30, 40, or even 50 years or more. The payload that can be delivered to distant dwarf planets is tiny compared to the total spacecraft mass, because most of the mass must be devoted to fuel and propulsion systems. Scientific instruments must be miniaturized and carefully selected to maximize the science return from limited resources. The radiation environment becomes increasingly harsh with distance from the Sun as the protective influence of the solar wind decreases. The extreme cold at distant dwarf planets and the vast distance make communication difficult, with signals taking many hours to reach Earth and data transmission rates severely limited by the weakness of signals from so far away. A spacecraft antenna at the edge of the solar system must transmit with limited power across a distance of billions of kilometers, and the signal that arrives at Earth is so faint that it must be collected by the largest antennas on the planet and amplified with sophisticated electronics to recover the data. These practical challenges explain why, despite more than 70 years of space exploration, humans have never sent a spacecraft beyond Pluto. The proposal to send a spacecraft to explore distant dwarf planets has generated considerable interest among planetary scientists, though the enormous challenges have prevented any mission from reaching the approved-for development stage. Hypothetical mission concepts have been designed to reach dwarf planets like Kawa, Gong, and Eris, though none has yet been selected for funding and development. A mission to Eris, one of the most massive dwarf planets, would require a launch in the coming decades to take advantage of favorable orbital geometry that will not repeat for centuries. Such a mission might take 30 or 40 years to reach its destination, requiring spacecraft systems designed for extreme longevity and reliability far exceeding anything built to date. Solar power would be insufficient at such vast distances, making radioisotope thermoelectric generators essential for powering scientific instruments. These generators convert the heat from radioactive decay into electrical power, allowing the spacecraft to function in near total darkness, where solar panels would produce almost no electricity. A preliminary study suggested that a mission to Eris might cost several $billion, making it comparable in scope and expense to the most ambitious planetary exploration missions ever conceived. Some mission concepts have proposed launching multiple smaller spacecraft rather than a single large probe, creating a distributed exploration network. that could observe different aspects of the dwarf planet system simultaneously. Others have suggested ballistic trajectory designs that would allow reaching multiple dwarf planets with a single spacecraft, though the timing would need to align with favorable orbital geometry occurring at decades-long intervals. Such multi-target missions would require extraordinary precision in trajectory planning to ensure the spacecraft arrives at each destination with the correct velocity and timing for scientific observations. The scientific value of such a mission would be extraordinary, potentially revealing the surface composition, internal structure, atmospheric properties, and geological history of a massive dwarf planet in unprecedented detail. Detailed images of surface features could reveal cryovolcanism, ice distributions, crater densities, and other characteristics impossible to determine from Earth-based observations. However, the long development timeline, enormous expense, and competing priorities for space exploration resources have prevented any such mission from advancing beyond the conceptual stage. The New Horizons spacecraft, having completed its primary mission at Pluto and conducted a detailed exploration of the small Kuiper Belt object, Arakoth, continues to transmit data and take observations as it journeys deeper into the outer solar system. The extended mission phase involves observations of dwarf planets and Kuiper Belt objects from large distances, taking advantage of the unique vantage point of a spacecraft traveling far from Earth. The spacecraft is now in a region where the interplanetary medium becomes increasingly sparse, and the environment transitions from the solar system's inner regions toward the heliopause, the boundary where the solar wind merges with the interstellar medium. New Horizons instruments continue to measure the properties of this region, studying cosmic rays, the solar wind, and the magnetic field environment. The spacecraft is positioned to observe stellar occultations, events where distant dwarf planets pass in front of background stars, as seen from the New Horizons vantage point. These occultations provide valuable geometric information about the sizes and shapes of dwarf planets, complementing observations from Earth. As New Horizons travels farther from Earth, its power source degrades gradually, with less radioisotope power available each year. This limits the instruments that can be powered and the frequency of observations, but the spacecraft is expected to function for at least another decade, potentially extending our knowledge of the Fifth to solar system for years to come. The extended mission also monitors stellar occultations of distant dwarf planets, contributing to an international effort involving multiple telescopes and space-based observers to characterize these distant worlds through precise geometric measurements of how they block starlight. The capabilities of future telescopes will dramatically expand the ability to study distant dwarf planets without the need for spacecraft visits. The James Webb Space Telescope, already making contributions to dwarf planet science through its infrared observations of Makemake and other objects, will continue to provide detailed spectroscopic observations impossible from ground-based telescopes. Its large mirror and sensitive detectors allow the detection of faint objects and the measurement of subtle spectroscopic features that reveal surface composition and temperature with unprecedented precision. Future ground-based telescopes, including the extremely large telescope currently under construction in Chile and the Giant Magellan Telescope being assembled, will provide unprecedented angular resolution for imaging and spectroscopy of faint solar system objects. These massive telescopes will be able to detect very subtle brightness changes in dwarf planets, revealing rotation rates and surface variations with precision unattainable with smaller instruments. Adaptive optics systems on these telescopes will compensate for the blurring effects of Earth's atmosphere, allowing ground-based observations nearly as sharp as space-based telescope imagery for bright objects. In the next few decades, it is possible that new telescopes might even detect the largest moons of distant dwarf planets directly, allowing precise measurements of their orbits and the calculation of system masses. Space-based observatories planned for the coming decades, including potential successors to the James Webb Space Telescope, will offer continued improvement in sensitivity and spectroscopic resolution. The combination of multiple observing techniques across different wavelengths will provide increasingly detailed information about surface compositions, internal structures, thermal properties, and potentially atmospheric compositions of the most distant and faintest dwarf planets and candidates. Each new observation adds another piece to the vast puzzle. The total population of dwarf planets in the outer solar system remains one of the great unknowns in solar system science. 5 dwarf planets are officially recognized, while numerous candidates likely qualify as dwarf planets based on their sizes and the likelihood that their gravity has shaped them into nearly round forms. However, the exact number of dwarf planet-sized objects in the Trans-Neptunian region remains unknown because observational surveys are incomplete. Many of the largest dwarf planet candidates have been discovered, but smaller dwarf planets may remain hidden among millions of smaller objects whose detection would require deeper surveys or more sensitive telescopes. The incompleteness of the current census results partly from the challenges of detecting faint objects and partly from historical accidents of discovery. Early surveys focused on certain regions of sky and certain orbital zones, creating a discovery bias. Objects in less explored regions may remain undetected. Additionally, dwarf planets with unusual colors or low reflectivity might be harder to detect than brighter objects with similar intrinsic sizes, meaning that some of the actual dwarf planets in the solar system could have sizes comparable to known objects, but have remained undetected because of their low reflectivity. The next generation of wide-field survey telescopes may detect tens or hundreds of additional dwarf planet candidates, expanding the inventory of known trans-Neptunian objects. Estimating the total population by extrapolating from the incompletely known sample requires careful correction for observational biases and detection limits. Current estimates suggest dozens of dwarf planets likely exist in the outer solar system, but this number is speculative and could change dramatically if major new surveys reveal a different population than has been detected historically. The boundary between the solar system and interstellar space remains a concept rather than a sharp, well-defined frontier. Planets and dwarf planets orbit in the realm dominated by the Sun's gravity, where the Sun's influence extends outward to enormous distances. The solar wind, a stream of charged particles flowing from the Sun, also carries the Sun's influence outward in an expanding bubble called the heliosphere. Beyond this bubble lies interstellar space, where the influence of distant stars and the galactic environment dominates. The exact location of this boundary depends on how it is defined. The heliopause, where the solar wind's outward pressure is balanced by the pressure of the interstellar medium, lies at perhaps 100 to 120 astronomical units from the Sun. Some dwarf planets and extreme trans-Neptunian objects orbit close to this boundary. Very distant detached objects like Sedna, with orbital distances approaching 100 astronomical units at aphelion, may move between the realm dominated by solar gravity and a region where stellar and galactic influences become significant. The Oort cloud, a hypothetical shell of icy planetesimals surrounding the solar system, extends from perhaps 2,000 to 100,000 astronomical units from the Sun, with some estimates placing the outer boundary even farther. However, the Oort cloud has never been directly observed and remains theoretical. Objects in the inner reaches of the Oort cloud, if it exists, would be only very loosely bound to the solar system, responding to gravitational perturbations from passing stars. A star passing within a few light-years of the solar system could scatter Oort cloud objects into the inner solar system or eject them entirely, creating transient comet storms. The boundary between the solar system proper and the vast interstellar ocean beyond it is not a wall, but rather a gradual transition, where the sun's gravity wanes and other influences gradually increase. The existence of these distant dwarf worlds and the lessons they teach reshape how astronomers understand the formation and evolution of planetary systems. The diversity of objects in the outer solar system, ranging from the massive Eris to the rapidly spinning Haumea with its rings, to the extremely distant Sedna, demonstrates that planet formation produces a far wider range of body types and orbital configurations than the simple inner solar system might suggest. The presence of dwarf planets in orbital resonances with Neptune indicates that planetary migration rearranged the outer solar system dramatically during the early solar system's evolution. The collisional families identified around certain dwarf planets provide evidence that large impacts have shaped the outer solar system, creating families of bodies that share common origins. The spectroscopic evidence for diverse surface compositions, including various ices and organic materials, reveals a rich chemical heritage preserved in the outer solar system's most ancient objects. Understanding how these bodies formed, migrated, collided, and evolved across billions of years informs our understanding of planetary systems generally. The same processes that created dwarf planets in the solar system also create them around other stars. Observing dwarf planets around distant stars could provide insights into planetary system architecture elsewhere in the universe. The small bodies and dwarf planets of the outer solar system may represent the building blocks from which planets form, providing fossils of planet formation processes. The fact that planetary growth was truncated at dwarf planet sizes in certain regions of the solar system, while progressing to full planets in others, tells us about the distribution of material and the timescales of planetary assembly in the early solar system. Each new observation of distant dwarf planets adds details to the rich tapestry of planetary system evolution. The stark and quiet beauty of the outer solar system remains largely inaccessible to human eyes, visible only through instruments and observations conducted from Earth or nearby space. Yet the dwarf worlds that inhabit this realm possess an aesthetic power that emerges from understanding their strange properties and exotic compositions. Haumea, the rapidly spinning, elongated dwarf planet ringed by frozen particles, represents a world reshaped by a cataclysmic collision into a form unlike any other body in the inner solar system. Makemake, bright and distant, reflects the sunlight with an alien purity, its surface coated with methane and nitrogen ice in forms unknown in the warm inner solar system. Eris, the most massive dwarf planet, travels through its eccentric orbit with a slow, stately motion, its highly inclined path marking it as a world displaced from its formation region into the scattered disk through gravitational encounters with Neptune. Sedna, more distant and extreme than Pluto itself, carries its orbit to regions so far from the Sun that stellar perturbations may influence its trajectory, making it a bridge between the solar system and interstellar space. Gongol, coated in reddish organic polymers, displays the accumulated radiation processing of billions of years of exposure to cosmic rays and ultraviolet light. Quaoar, bearing a remarkable ring system that challenges simplified models of ring survival, suggests that the outer solar system contains more complexity and richness than models anticipated. These worlds exist in a realm of profound darkness and extreme cold, where the sun appears as an unremarkable star among millions. The landscape of each dwarf planet remains essentially unknown, hidden beneath layers of ice and uncertainty. Yet through patient observation, careful reasoning, and technological advancement, astronomers gradually illuminate these distant worlds, revealing hints of their compositions, structures, and histories. The patient work of studying these distant dwarf worlds continues steadily, driven by the fundamental human curiosity to understand our place in the cosmos and the processes that shape planetary systems. The observations accumulate gradually, each measurement adding a piece to an incompletely known puzzle. Spectroscopic surveys reveal the presence of new ice species and organic compounds on distant surfaces, expanding the inventory of known materials in the outer solar system. Stellar occultation campaigns coordinated across multiple continents reveal the precise sizes and shapes of dwarf planets, with geometric precision impossible to achieve through other methods. Moon discoveries show that these worlds sometimes possess satellite systems of their own, gravity binding smaller bodies into orbits around larger ones. Ring systems surprise astronomers with their presence and unexpected properties, challenging theories of ring stability and formation. Each new finding raises new questions and clarifies aspects of these distant worlds that had remained mysterious. The dwarf planets and dwarf planet candidates beyond Pluto represent laboratories for understanding planetary science, worlds that challenge assumptions and expand knowledge about how celestial bodies form, evolve, and age across cosmic timescales. The strangeness of these worlds lies not in any supernatural quality, but in their genuine unusual properties when viewed through the lens of what was previously known about the solar system. Haumea's rapid rotation, Eris's extreme orbit, Quaoar's unexpected rings, and Sedna's extreme distance all represent observed realities that pushed astronomers to expand their understanding and refine their models. The work continues in the quiet darkness of observatories and computational laboratories around the world, patient and persistent, gradually revealing the nature of the strange dwarf worlds beyond Pluto. As telescopes improve and new discoveries emerge, the inventory of known dwarf planets will grow, and the understanding of the outer solar system will deepen. The mysteries that remain far outnumber the answers currently in hand, and that vast expanse of the unknown makes the study of these distant worlds endlessly fascinating. The outer solar system will continue to reward patient observation and careful analysis, revealing secrets preserved in the cold realm beyond Neptune, where dwarf worlds follow their ancient orbits through the darkness.